Speaker, the final one of this session, is Tim Bertram, who's going to tell us about, finally, to the reactivity side of these complex systems. And so he'll be telling us about ways that they're probing the heterogeneous reactivity of sea spray particles.
Okay, so I'd like to really thank Vicki and Kim for this invitation to come and share some of our insight into these questions. I take advantage of the fact that everyone has given a great introduction here, but I also take the challenge in trying to link some of these things back together in terms of how we can ultimately bridge these really disparate time and length scales. And this is where much of my research in my research group at UCSD focuses on, is how do we bridge these more molecular level images and discussions where we can ask interesting questions and probe individual particles with these large-scale global climate models that operate on time and length scales that are orders and orders and orders of magnitude much larger. So we like to think and ask questions here and probe here, but we often are guided by these large-scale biogeochemical questions that are answered on these large scales. And so this length here is a little bit too long at times and leads to a lot of challenging discourse. And I link this to sort of a challenging discourse that's also at my kitchen table in terms of linking between my daughter and my son, who have these different approaches to thinking about a common question that might be, how do I get food, right? And as they interact, they sort of progress in these types of states. Okay? And so the challenge here is, how do we construct this link? How do we think about this link? And at what point do these chemical reactions or phase transformations that are evident here have an impact on these larger scales? And so that's what I want to focus on today, is thinking about these processes that happen in the middle, right? And so how can we use these various laboratory, or moreover even macroscopic laboratory, or even field observation? So how can we probe heterogeneous reactions or multi-phase processes actually in situ in the field to provide these connections and actually guide backwards to think about what we need to know from these detailed systems, or what is essentially a detail that we don't need to know. And I want to make the point here of really thinking about heterogeneous chemistry or multi-phase chemistry, and the point of this talk is to think about how mixing state of aerosol particles impacts heterogeneous chemistry. And this is really similar to thinking about a box of chocolates. And so this box of chocolate here, this is an externally mixed box of chocolates, right? Each individual piece is different, right? And if we wanted to calculate out the chocolate removal rate from this box, we'd have a rate constant for each one of these individual chocolates, right? I mean, some of these go really fast, we know that. And some of these, like at least in my house, they're going to stay there for the rest of the year, right? But we need to know the rate constant for the removal rate of each one of these pieces of chocolate, right? If we want to be able to model this externally mixed box of chocolate. Now, if you have an internally mixed box of chocolate, right, you don't need to know all that much. If I want to calculate the chocolate removal rate from this box, I need to know the rate constant for each one of these pieces. They're all the same. Maybe there's some smushing on the edges, but for the most part, this is a reduced system. Now, the question becomes is how we think about our boxes of chocolate. We could argue perhaps maybe these two boxes of chocolate have the same average ingredients, right? They have the same amount of chocolate, they have the same amount of orange, or they have the same amount of lemon or whatever, but it's just all mixed up here, right? So if we measure this, right, and we measure this, and we think about the removal mechanisms for them, while they still may have the same average ingredients, the removal rates could be dramatically different, right? Some of these get picked out really fast, some get picked out slow, and it doesn't necessarily average. The average concentration may, but the average rates do not. And that's the question we want to get at today, is thinking about how do we bridge this specific disconnect. And so specifically, we're not thinking about chocolate, we're thinking about particles. And I'm not going to, this is the only, I know my title slide has some things about X-rays, but we're not going to talk about X-rays today. This is really just an image that follows up really nicely on what Lex just presented. And this is a carbon map. This was from Ryan Moffat and also some work done by Andy Andre, of looking at the individual sea spray particles, and this is a carbon map. And so the idea here, of course, is this is a significantly simplified system. This is just sea spray aerosol, although it's incredibly complex already. So you have these wide variability in the amount of carbon that's on each one of these particles. And the question is, do we need to study the reaction on each one of these individually, or can we just take the average approach? And how well does that work? Okay. So I'm going to come back to actually here something that was brought up in Alan Bertram's talk, and this was this reaction of N2O5 with various particle surfaces. And I'll provide a little bit of a broader context for this because my entire talk is going to be about N2O5, and for a couple different reasons. One is because it's kind of a nice probe of these surfaces, so you can learn a lot from it. And two is it's highly relevant. And so this chemical process here is something that's actually happening right outside, not during the day, but at night. So it'll happen this evening once everyone goes to bed. But the nitrogen oxides that are formed through any type of high temperature combustion, that's basically breaking apart N2 and O2, you make nitric oxide and NO2 ultimately. They react together to make ozone, NO2 and ozone, to make this nitrate radical that comes into this thermal equilibrium with N2O5. And we call this the nighttime nocturnal NOx reservoir. So it's really what we want to know is what's the fate of this big reservoir. If nothing happens to it, the sun comes up and it dumps all of this material back into this pool, and this can continue on and make things like tropospheric ozone that we're really interested in. But where this links in with aerosol particles is that the loss rate of N2O5 is primarily through a hydrolysis process. The rate-limiting step is hydrolysis of this molecule, right? So this doesn't happen in the gas phase. You need probably 4 or 5 water molecules around that thing to break it apart. So this primarily is catalyzed in the surface of an aerosol particle. So you need some surface, or it can be the surface of a building or the surface of the ocean. But if you're thinking about particles, it's happening on the surface of that particle. And we're even further interested in what happens as it goes forward. If there's chloride on this, you can make this molecule nitrile chloride, and that falls apart to make a chlorine atom. So you can take chloride to chlorine atoms. That's an interesting process. And you can also regenerate these nitrogen oxides. So what we want to know is this rate. So a lot of this talk is going to be about this rate. And we're going to talk about that often in terms of an uptake coefficient, gamma, and that's just a surface area normalized rate, right? So it's basically just the number of molecules removed by the condensed phase divided by those that strike the surface. So 1 means every collision is reactive, 0.1 means 1 in 10. Now, people often will say, well, you know, Tim, you study a boutique molecule. This doesn't really matter. I've never even heard of this thing. Well, the reality is that if you go into a chemical transport model, somewhere between 30 and 50% of these nitrogen oxides that are emitted are lost through these nocturnal mechanisms. So if we don't know that rate, this loss rate is a big component of that entire loss mechanism, if we don't know that rate here, then we don't know where 30 to 50% of these nitrogen oxides go. So that's kind of a big deal. And that rate, of course, depends on the surface composition of these particles. It depends on phase. It depends on the chemical composition, all these details. So it's not a detail, this process. It's really actually quite important. Okay, so the question that we're going to ask here is really what is this mechanism and how can we utilize things about single particle approaches or bulk particle approaches to sort of further push our ideas of this. And so if you think about what's actually happening with this molecule as it hits the surface, right? So a fraction of this is accommodated into the surface and then this dissociates out and makes this nitronium ion and nitrate. And the focus of what we're thinking about is really the fate of this little guy here. And so I'm drawing this in the middle of the particle. This might actually be occurring right on the edge of the particle here. It depends upon diffusion and all of the other processes that occur in these regions. And so the fate of this thing really depends on what else is in the particle in the region that it's formed, right? So if it's formed in a nice aqueous particle like this, well, it could react with nitrate and push it back. If there's a stronger nucleophile, if chloride's in the system, it can go through this channel that we were interested in before. Or it might just go forward and end up acidifying and end up adding a nitrate. So this is a neat mechanism if you're in the laboratory because you can make this reaction basically do whatever you want. You can change the relative humidity, you can change this reaction probability, you can change the chemical composition in here, and you can change the reaction probability. But it becomes really a headache for thinking about how you can communicate this sort of up that ladder. So this is a really interesting example of why single particles may matter is because it's dependent on the relative concentrations of each one of these constituents in this particle, right? So if you make that average assumption over the entire box of chocolates, you're going to assume every particle is the same average nitrate or chloride or water or whatever you have. And you may dramatically misrepresent this process. You may not. That's the question we're after today. So the question ends up being really, what's the fate of this guy in this matrix? Okay? And then sort of a further complication you can put on this is that these aerosol particles that live out here, they may not just be these aqueous inorganic systems. They may have nice surfactants that sit on the edges of this. Vicki talked a little bit about this already, and actually this data set here is from Bertram, where he basically showed that you could change the chain length of these surfactants, or you could make them straight chain or branched, and you could control basically that reactive uptake coefficient. And that's a really interesting result to this. But the real headache, or sort of the elephant in the room, is what these various phase transformations and these liquid-liquid phase separations, how they may impact N2O5 reactions. And so whether or not these thick organic films exist, at what relative humidities they exist, and ultimately how fast does N2O5 move through these films. And so you have all of these different controlling factors that are going to impact this rate. And the idea is, how can we represent these types of controlling factors so that we can get a better idea of what that process is? Okay, so I'll run through this really quick, but the idea here is if we understand the fate of this guy here, and so basically if we understand the kinetics for each one of these individual components, we can build a model for this system. And so briefly what we do is we build that model, and we build that on the fate of this NO2+. So we can represent its production in loss terms. We assume that's in steady state. And we can go through a bunch of math and we can come up with a parameterization, and I don't want to spend any time or labor over this, but we can come up with a parameterization for this uptake coefficient that's based upon liquid water content or nitrate, chloride. And we can represent this system either on an average case, so we average the entire aerosol population, or we could do it on a single particle case. Okay. And so what's nice about this type of parameterization here is that you can utilize this to go back and look at 15, 20 years of laboratory data and see how this works. And so if you look at this is the parameterized value, and this is that's measured in the laboratory. It does really well. It actually does exceptionally well, with the exception of a few measurements from the literature. What's you'll see already void from this is there's really very few measurements that are done on these more complex organic matrices within these parameterizations. Okay, so the idea of why I like something as simple as this is because you can actually take an expression like this and you can put that in a global model. Right? So this is what's in one of the global models, or at least it's an option for a parameterization in a global model, is the ability to take that type of information and run it through these chemical transport models and actually make global fields of these reaction rates. So the question is this a valid approach? Can we utilize this type of idea? Okay. So what I'm going to talk about today is really how do we measure this value here in this type of state, right? So in the native environment, so we're not measuring this on surrogate systems. We're trying to do this on ambient aerosol particles, and we're going to simultaneously measure the chemical composition of the aerosol particles in a bulk sense and a single particle sense, and see whether or not we get some closure between those systems using this kind of parameterization as a guide. So the question here is really how do we measure this N2O5 uptake coefficient? And the first step is you get a really good graduate student. And so this is my graduate student, Olivia Ryder, here. And she's the one that's driven this entire piece of work, so I can't take credit for it. So how do we do this? Basically, these are direct measurements of this N2O5 uptake coefficient. What we do is we take ambient aerosol particles and we bring those into a large-scale flow reactor. So we're basically bringing in the ambient particles, and we're entraining into that system a wide number of reactive trace gases, so whatever your choice is. In this case, it's N2O5. We add that into the system, and we basically allow them to steep in N2O5. Okay? And now steep, I mean, is sort of a slight word because we're not trying to change the chemical composition that much. We're basically trying to probe that rate. So we only add a small amount of N2O5 to the system. We add in about a part per billion or so when these experiments are done in their optimal sense. And that allows us not to build up or basically change the chemical composition of the particles extensively during the course of this reaction, but just probe that initial uptake rate. And so we take those particles, and what we monitor at the base of this is we monitor N2O5 directly. So we monitor N2O5 in the gas phase. We can see how much N2O5 is lost to these aerosol particles. And then we also measure the particle chemical composition. And when I say we, this is Kim Prather's group. In the case of these experiments, this was her graduate student, Liz Fitzgerald. And so what we can measure is the N2O5 that's lost to those particles, and we can measure the production of various other compounds from those particle surfaces. And the Prather group is measuring the particle composition before and after reaction. We'll come back to that in a bit. Okay, so how do we do this from the measurement of the N2O5? We do this by chemical ionization, time of flight mass spec, and so this is not necessarily a handheld mass spec. It's a little bit larger than that. The TOF on this is about the size of a shoebox, and that's manufactured by TOFWork in Switzerland. And we've worked with them and Aerodyne out of Boston to work on interfaces to be able to make these chemical ionization front ends that can work toward very specific measurements of these trace gases in the atmosphere. And so in this case, most of the work that I'll describe here, we use I- as a reagent ion. So we add methyl iodide over a polonium source and make those reagent ions. We mix that in with the analyte, right? So that's the gas stream. We make our ions, and basically we just move them to the TOF mass analyzer. What we get from this is a really nice selective measurement for N2O5. This is a very soft ionization mechanism. So we actually see the I- N2O5 adduct. So we don't see fragments of this. We don't see it as NO3- or whatnot. We see it actually as that specific guy. And we also see the products, right? So this is I- ClNO2 here, and that's I- N2O5, so we get this in each individual shot. And this is a nice way of looking at reactant product pairs in the same instrument. So if we have any small biases in these measurements, we can be able to correct for those. So the end products of this, or what do we have? This actually does become important to have a very sensitive instrument and a reasonably accurate instrument. This is not a high-resolution instrument, but it allows us to do this reaction under ambient conditions, and that's important for interpreting these results. Okay, so how we actually do this is one of the challenges is this flow reactor actually has quite a long reaction time. It has about an 8 or 10 minute reaction time. And the frustrating part of that is oftentimes the atmosphere varies on that time scale. And so what we're doing here is instead of measuring these really long decays that you would do by changing the interaction time of your gas phase molecule with the particles, we actually just modulate the particles on and off and watch for that change in the N2O5 concentration. And from that, we can go backwards and calculate out this loss rate. So we change that surface area back and forth. And what's challenging about this is it's a different regime than what you would initially look at if you were doing a laboratory experiment. So this loss rate as a function of surface area, of course the slope of this line gives you that uptake coefficient. If you do this in a laboratory sense, you oftentimes just crank up the surface area that you have. And that's nice and that's fair. I mean, that's actually the way that you get at these initial uptake coefficients. But when you do this in the atmosphere, you don't have that option. You get the surface area that you get, and the surface area you get is way down here, right? So that's a challenge, and that's why you need these sensitive instrumentation, this set of sensitive instrumentation to be able to look in this regime. So we're dealing with about 100 microns squared per centimeter cubed in a range over that. This is just from one data set in Seattle. And so the question is, does this work? And so here's just a laboratory calibration of this. Again, this is over the surface area range from 0 to about 1,500. So that's about the range that you would get in the atmosphere in any urban environment. And this is for malonic acid, something we've heard a lot about today. So it's a pretty soluble diacid. And you see this, the uptake coefficient here that we retrieve from this method is very consistent with what you would get if you extrapolated the surface area concentrations several orders of magnitude higher. And then, of course, if we shut down the relative humidity down to about 0%, again, this is the first step of this reaction is a hydrolysis reaction. You can turn this reaction off. And so we have some pretty good confidence, about 20% with previous observations, that we can do this measurement in these really low surface area environments. Okay, so what happens when you make this measurement? Well, you go out to places like the Scripps Pier, and you measure this uptake coefficient. You measure it for 2 weeks, 3 weeks, as long as you want to. And you can basically build up a distribution of, this is just a frequency of measurement, as a function of gamma N2O5, and you find out that it's a broad function. Not too surprising, right? There's a wide range of chemical compositions that are out here, a wide range of relative humidities. And what we can do is say, well, let's take this nifty little parameterization that we developed from the laboratory experiments, so it's basically constrained by all of the laboratory measurements that we know, and we're going to take the population averages for each one of these components. And of course, one of the sticklers here is what do we know actually about the liquid water content. And we're going to take that population average and we're going to stick it in, and we're going to see if that parameterization can match these. And it almost never does. It's always high in this component. And so that really leaves us with two things that could drive this process. One is, well, maybe the single particle composition is what's important here, right? So maybe we actually have to resolve this parameterization on an individual particle level. So that's something we could test. And the second thing that I'm not going to talk about in this talk is whether or not we need to invoke those organic films to be able to provide this suppression, right? And so that's really an ongoing effort. Okay, so if we go back to this picture, Kim showed this already earlier today, we really have this idea of revisiting mixing state where one mixture might look like this, right, this internally mixed population, and the other mixture might look like this externally mixed population. And the question we want to ask really is, while these may have the same average composition, they probably have different average reactivity, and how much does that matter? So one way to look at that, just in a cartoon type sense, is to look at these three different populations. So if you were actually to count up all the nitrates in here and count up all the chlorides in there, you'd find that each one of these have the same population average chloride to nitrate. Should be about 1. Okay? And our question here is, of course, this chloride to nitrate ratio is what we think is a really big factor for driving this uptake coefficient from just the inorganic perspective. And so these three distributions, though, while they have the average of 1, they could be distributed in various different ways, right? So this one here looks a little bit like this. There's some that have more than 1, some that have less than 1. This guy here is much more broad distribution. Of course, they just show a subset of this, where some have a factor of 10 over here in the ratio, some are 0.1. And then, of course, you could have this third distribution where almost none of the particles have this exact value of 1. They all live out at the extremes, or none of them have that value, right? And so we've seen already from Kim and Vicky's talks today that the atmosphere can range widely between these different representations, even for the inorganic ions. Okay, so does this matter for N2O5? This is sort of another vision of that parameterization. So this color map here, I'll walk through this quite slowly, is the calculated uptake coefficient. So this is from that parameterization. This is so the color is that value. And the x-axis here is the ratio of chloride to nitrate. And the y-axis here is the ratio of water to nitrate. So something like a nascent sea spray particle, something that's made in that wave channel, is going to be way up here, right? It's almost all, in terms of the inorganic component, lots of chloride, a lot of water on those particles. And as this moves in time, or as it ages in the atmosphere, as Vicky was describing, it usually ends up somewhere over here, right? Somewhere on this plane, right? Nitric acid's driving this process. You're adding more nitrate to the system, or even these organic acids that Alexei was talking about drive you from here somewhere into these spaces. So as a function of time, that uptake coefficient we think is going to go down. So for example, if you had these two populations right here, so they both have the same average nitrate to chloride ratio. So this is for one of these planes. But they have, one is a distribution, right? As you would expect in the atmosphere, you're going to have a distribution of chloride to nitrate. But one of them is just, the average case. And you run that through this calculation or this parameterization, you're going to have a change in that uptake coefficient. Basically because these guys react quite fast, these guys react quite slow, and it doesn't actually average out in the way that you might expect. So what happens when we actually go to real particles? So this is some older data from Kim Prather's group where we go back and look at the individual chemical composition, right? So we're going to go back and we're going to look at the chloride to nitrate ratio here. And we're going to look at this in 3 different types of air masses. So one is nascent sea spray. So this is not an old data set. This is actually what came out of that wave channel. And this is going to live way over here where there's almost no nitrate on this system, okay? So if we look in this space. And we look at Jeju Island in Korea. This actually is somewhat in between here, right? The average value for this is a little less than 1, right? So there's a mixing of fresh sea spray in this region and aged sea spray in this region. And then if you go all the way to Long Beach, this is an air mass where you might have some sea spray, but it's sitting in a giant nitrogen oxide plume, and the average value is going to be way down here, right? So this is just in terms of the population average. And what I lay on top of here is what the uptake coefficient should be based upon our parameterization. Now, if you actually go and you utilize the single particle measurements as they should be instead of just taking all of them and averaging them together, which I'm sure makes Kim's blood boil when we do that, you see something like this, right? This is what it really looks like. You have this wide function here where you have mixing of fresh particles and aged particles, and it's really just a big soup, right? And there's some driving of this based upon temporal variability, but even if you take a snapshot that's relatively short, you get something that's similar to this. As opposed to Long Beach also, it's something more along these lines here. So if you go through and you actually take each individual particle and you calculate out using the parameterization of ours, and you look at this, you're going to get a different perspective from this, right? So you're going to have a range in these uptake coefficients as a function of these individual particle states. So this is basically the formulation of this idea. Now, unfortunately, for Jeju Island or Long Beach in these cases, on these ambient samples that were done here, we didn't have this simultaneous measurement of the N2O5 reactivity. So we'll use a slightly different data set for that. And that's actually this data set that I described already here. Actually, this is a collection of a couple data sets as well. And so the idea here is basically, can we use a case study here for Scripps Peer where we have all these things done simultaneously? So we have the single particle chemical composition, we have the N2O5 uptake coefficient that's done on the entire population, and can we merge these scales together, and what pieces of information do we have, and what pieces of information do we really need to add to this? So there are three. I'll take this as a case study, and there are three specific days that we can look at. So the difference between doing these calculated laboratory experiments and doing things in the native environment is that we can't put compound X or compound Y into the beaker and make the particle population change. We basically have to wait for the atmosphere to change the particle composition for us. And because of that, you might have to wait many days for this to occur, but it does happen, specifically in these chemically rich environments such as we have in Southern California. And so here's just a transect of 3 different days here. So we have a first day here that's relatively polluted, and what all these little color dots on here are where the air mass actually was over the past 24 hours. And what's happening in this first day that's polluted is their air mass is just basically sitting right offshore of San Diego, and it's going back and forth. Okay? And the second day here, this air mass had basically swept around Los Angeles and came right in here. And this third day, it looks pretty similar to the second day, but it's actually entrained a little bit of this plume. You can't see the chemical plume that comes in from Los Angeles here, right? So Los Angeles up here, San Diego down here. And if we look at the uptake coefficient here, these are these red triangles here, just over those 3 time periods. You see on this first day when you have this large amount of pollution, this value is somewhat suppressed by about a factor of 3 from what you would expect on pure salt, as opposed to this clean day when you're up really on something that looks like sodium chloride. And this third day, a little bit of a mix. And so we'll concentrate our focus on these 2 days here and think about if we can explain that variability based upon average chemical composition, or if we need to invoke single particle chemical composition, or if even that is not enough. Okay, so coming back to the same type of perspective, we have these 2 regions. We have this first region here in this pink line, that's the polluted case, and we have this region here, this blue line, and that's the combination of regions 2 and 3, so that's really that unpolluted or cleaner air mass. And we measure the N2O5 uptake coefficient in these 2 regions, right? So in region 1, it's a little bit less than 0.01, and in region 2 and 3, it's like 0.035 or 0.028, okay? Now, if you take the average ensemble concentration for this, so the population average for nitrate and chloride and what we think for water as well, if we solve for that concentration, we put this into this model, what you would find is that in every single case you measure that you would calculate this to be high, right? So you're basically a factor of 3 high in this first region. So the question is, if we put in the actual distribution here, do we do any better in these cases? So all these lines here, now this is the actual distribution of chloride to nitrate from this single particle measurement of Kim Prather, and for both these couple different periods. And you find if you run this full calculation here, is you do a little bit better. You get it down to 0.02. You can't go all the way down to replicating the actual results here. While in these second and third regions, you get about the same value for the two of them. So it's helpful, and it's getting us closer, but it does not actually replicate the entire set of the observations here. So it's certainly a region of the atmosphere where utilizing the single particle chemical composition is helpful, and it's working us toward that area. But the reality is that the rest of the particles that we are not probing right now are probably doing the rest of the work in terms of changing that reaction. And so the last few minutes here, I'll just focus on the particles themselves and what happened to those particles in the reactor. And as you can see through these two images here, so this is just the PDF, or just think of it as the frequency distribution of the chloride to nitrate ratio for this period 1 and this period 2. In blue is the ambient particles, and in the green are the particles that have been exposed to N2O5. You can see in both of these cases we really didn't change the particle composition at all in the reactor. That's actually was by design. We did not want to invoke a dramatic change in the particle chemical composition because that in turn is going to impact its reactivity. So we try to do this really lightly so that we don't change the composition of the particles in the reactor. We're only just adding a small amount of nitrogen to each one of those systems. So this is the reason we do this, is because we're looking at the gas phase signal, that decline in N2O5. But if we wanted to revisit this experiment and do it from a single particle perspective, what you'd actually want to do is try to increase the concentration of your target reactant. And so if you do that, well, one, for this N2O5 system, it ends up being a really hard experiment because it's hard to generate high concentrations of N2O5 without simultaneously generating high concentrations of nitric acid. So this system that we're looking at here also has nitric acid within it. But if you look at, for example, these nascent particles here, so this is right out of the sea spray generator, right, and these really high chloride to nitrate. And if we basically add enough of this mixture of N2O5 and nitric acid to the system and wait long enough, you'll see them move in this space, sort of exactly as Kim and Vicki had discussed previously. And the question here is, do each individual particle move from being rich in this, or high in chloride to nitrate, to being low in chloride to nitrate the same way? And for that, we can try to look at the other coordinates of that particle. And so this is a little bit of a busy slide here, but now I'm focusing on the y-axis of the single particle chloride to nitrate ratio, right? So each one of these individual dots is a single particle, right? So there are thousands of particles on this plot. And the blue here is the nascent, so these are right out of the sea spray generator, and there's a little shift here that we're still trying to understand here of what that chloride to nitrate signal is, okay? So this is just the signal here. And this is plotted as a function of the organic mass fraction. So this is the organic signal from each one of those individual particles, right? So this particle here has a chloride to nitrate and it has an organic component to it. And so this is that collection of those nascent particles. And then when we add in the nitric acid to the system, we can see, well, for these guys that have a small amount of organics, we see a big drop in that. But as we increase this organic mass fraction up to some point where maybe it's 0.1 or 0.2 in these regimes, you can see that there's very little change. So this is the sort of parallel plot to what Vicki was showing in her couple different particle types, but it also shows you for this collection of all of these types of particles what that convergence is going to be. And it also tells you where all of those particles actually live. So for example, in this experiment, what we were looking at here is for those nascent ones, there's actually, if you're just looking at this population here, there's actually very few particles that live out in this region of having enough organic to suppress that. Most of them live out in this region, and you'd see them reacting away. Okay, so the conclusions that we have for this, there's basically three. One is including this chemical mixing state into existing parameterizations. It helps close that gap a little bit, not completely. Ongoing work really needs to be focused on single particle variability in the organic component of this. So really going back and thinking about whether or not those relationships of, for example, the organic to carbon ratio on the single particles could be utilized within this type of parameterization. And then Finally, the future work on this is trying to think about how you can run these experiments simultaneously. So you can simultaneously look at the loss of N2O5 and that uptake coefficient that you can get quantitatively from the gas phase measurements, and compare that to what you could learn from aerosol measurements where you're looking at that accumulation of nitrogen. And then as a takeaway on this, I also want to stress on this that this reaction is quite important, both from an air quality perspective, but also from a climate perspective. And this is the challenge that we're dealing with, is that if on this x-axis is the N2O5 reactive uptake coefficient, laboratory measurements can basically tune this all over the map. You can make it about 5 orders of magnitude depending on what you put on that particle. Ambient observations show this to be a little bit narrower, but the current global climate models have this pinned in this pretty narrow region. So if you take any parameterization of this reaction, you put it in a climate model, you're going to end up somewhere around here. And then if you assess the sensitivity of the model in metrics that we care quite a bit about to this reactive uptake coefficient, this is something that Matt Evans had done, you can look at the global change in ozone, global change in OH, and actually the lifetime of methane, the second most important greenhouse gas, as a function of this. So beyond just air quality, even if we're thinking about climate, this can have a reasonably large impact, just one reaction. And so with that, I'd like to leave my acknowledgments. Of course, my graduate student Olivia Ryder did much of this. The SIMS development was a large collaborative effort from our part. And this N2O5 reactivity measurement that we've been talking about has leveraged a lot of expertise from Kim's group, specifically on the ATOF-MS component. And then funding from DOE, and then, of course, the Center for Aerosol Impacts on Climate. Yeah.
Okay, we have time for a question or two. We're at the end, so. Alan.
How close do we have to get between the model and the observations before you're happy? Does it have to be perfect? Or?
No. The problem is that at almost every model, this is really favorable. Almost every model, if you went back and looked at that GeoScan image file, there's that image there. It's 0.03 almost everywhere. Every measurement that we make, if you look back at the frequency distribution of that coefficient, Steve Brown's work of using statistics, every one of those is 1 order of magnitude, at least if not 2 orders of magnitude lower. So I think reality, currently we're in here in both global models and in regional models, and I think reality is probably someplace down here. I will be happy when I see a distribution in the model as opposed to a single value, even if the parameterization should give you a distribution. Okay.
Are there any other questions, or people are hungry now? Probably hungry now. Okay. Well, if not, let's thank all of our speakers. This was a fantastic session, and I really want to thank everybody, so thank you. Good job. That was good. Have my